A river looks like the most permanent line on a map. Roads bend around it, cities face it, borders borrow it. Then, sometimes in a single flood, the river leaves that line and starts using another one. Not a bend creeping sideways by a few meters each year. The main channel can jump kilometers across its floodplain and pour into a route that was dry, minor, or forgotten the day before. In August 2008, the Kosi River broke through an embankment near the Nepal-India border and reoccupied an older path across Bihar. From space, the change looked less like a river overflowing and more like somebody had drawn a new river across the land. Water spread through places organized around the old channel because the system's map had changed underneath them. Geologists call this an avulsion. The word matters because an avulsion is not ordinary river motion. A meander migrates as erosion works on one bank and sediment accumulates on the other. An avulsion is a state switch. The old route can lose the flow while a new route captures it. That sounds random. It is not. The flood may provide the final shove, but the river has usually spent decades or centuries preparing the jump. Every grain it carries, every levee it builds, and every kilometer of low floodplain beside it changes which route is easiest. The strange part is that the river creates the condition that can make its own channel obsolete. It builds upward, it stores a shorter route nearby. Then a small connection can unlock a much larger reorganization. To see why, stop thinking of a river as a line. Think of it as a moving layer of water and sediment constructing a landscape beneath itself. The switch can happen at almost any human scale. A small distributary may abandon one field for another. A mountain stream can jump across its fan. A continental river can redirect the water and sediment of an enormous basin. The geometry is different, but the question is the same. When does the current path stop being the easiest path? Answering that requires three views at once: the map, the cross-section, and the moving sediment budget. Flowing water carries sediment in several ways. Fine material rides suspended in the water. Sand skips and rolls along the bed. During a flood, the river has enough energy to move far more of both. But when the water spreads, slows, or reaches gentler ground, some of that load falls out. Inside the channel, deposited sand forms bars. Along the banks, floodwater loses speed and drops its coarser grains first. Repeated floods can build natural levees, low ridges that run beside the channel. Farther away, finer mud settles across the floodplain. Now watch the accounting. Sediment enters a reach. If the river cannot export all of it, the excess stays. The bed rises. Geologists call this aggradation. The water surface rises with it, and the natural levees can rise too. The channel is no longer cut into the lowest part of the valley. It is slowly building a raised corridor. In cross-section, the geometry is almost upside down. The active river can sit above parts of the floodplain it appears to drain. That arrangement is common on sediment-rich fans and deltas. The channel remains in place because its banks and levees contain it, not because it occupies the only low route. This is the river's memory. A floodplain preserves old channels as shallow swales. Former river paths may fill with vegetation and farms, but they can remain lower and steeper than the modern channel. The present river keeps adding sediment to itself, while yesterday's routes wait beside it. So each flood does two opposite things. It reinforces the current route by rebuilding its banks, and it can make that route less efficient by raising the bed. The river is constructing both its stability and the reason that stability may eventually fail. To predict an avulsion, researchers measure a quantity called superelevation. Draw the channel bed, draw the nearby floodplain. The vertical difference between them tells you how high the river has perched above an alternative surface. Then compare that height with the depth of the channel itself. A shallow river raised by 1 meter is not in the same state as a 10-meter deep river raised by 1 meter. The ratio matters because it sets how much gravitational drop becomes available if water escapes over the bank. Across field sites and experiments, avulsions often occur after the bed has risen by an order 1 fraction of the channel depth, commonly around 1/2. That is not a magic universal number. Bank strength, vegetation, flood magnitude, and local topography matter. But the pattern is powerful. The system tends to switch after it has built enough relief to make another route competitive. A flood raises the water above the natural levee. At first the spill is only a thin sheet. If it finds an old channel or a low depression, the sheet concentrates. Concentrated water erodes. The notch deepens, which pulls in more water, which deepens the notch faster. That is the threshold crossing. Before it, most disturbances drain back into the old channel. After it, the breach can connect the river to a path with greater slope. The new path no longer needs a larger flood to grow. The path itself creates the advantage. A river can spend centuries approaching this geometry and hours crossing it. The long wait and sudden motion are not contradictory. They are what a slow system with a threshold looks like. For years, a useful rule said that avulsions cluster near a special downstream zone called the backwater reach. Near the coast, the ocean influences the river's water surface far upstream. Flow slows, sediment accumulates, and the channel can become especially prone to switching. That rule works well for many lowland deltas. The river approaches standing water, loses transport capacity, and builds sediment within a broad zone. An avulsion there creates a new delta lobe, moving the river mouth without requiring the breach to begin at the shoreline. But rivers on steep alluvial fans behave differently. They leave a mountain valley and spread onto open ground. Sediment is dumped near the fan apex, where confinement ends and slope changes sharply. Channels can avulse close to that upstream transition instead of near a coastal backwater zone. A 2024 synthesis in Nature reconciled these patterns. The controlling question is not one fixed distance from the mouth. It is how sediment deposition and floodplain geometry vary downstream. Different landscapes create different zones where the channel becomes super elevated and where a new path can gain slope. Put a fan and a delta side by side. On the fan, likely avulsion sites cluster near the apex. On the delta, they can cluster within the backwater-influenced reach. The same threshold of behavior sits inside two different spatial rules. That distinction changes risk maps. Marking every kilometer equally misses the mechanism. The dangerous location is where the landscape helps the river build high, and where an escape route can fall away faster than the channel it leaves. Location is only half of the prediction. Once a breach forms, the new path depends on the topographic surface around it. On a steep fan, water may run nearly straight down the maximum slope. On a lowland delta, subtle ridges, abandoned channels, roads and levees can redirect it. Modern elevation data can reveal those pathways, but centimeters of error matter when the whole floodplain differs by only a few meters. The route is constrained, not predetermined. Imagine one river feeding a fork. The old branch is long and gentle. The new branch is short and steep. At first, almost all the water stays in the old branch because the new connection is narrow. A little more water enters the new path. Faster flow erodes its bed and widens its entrance. That lowers resistance. Lower resistance sends still more water into the new path. The split is not passive. It is a feedback loop. Sediment strengthens the switch. The old channel receives less water, so it may lose the capacity to carry its sediment load. Bars grow. The bed becomes rougher or shallower. Meanwhile, the new channel scours and becomes easier to use. Erosion can also move upstream as a head cut, a step in the bed that migrates toward the breach. Each retreat lengthens the efficiently drained reach. The capture front walks backward while the new channel grows forward. Eventually, the new path carries most of the discharge. The old river does not necessarily vanish. It may persist as a smaller distributary, a lake-like reach, or a chain of wetlands. But the network has changed state. The main stem now points somewhere else. This is why a breach can outrun attempts to close it. Engineers are not plugging a static hole. They are competing with a feedback that is enlarging the hole, lowering the new route and starving the old route at the same time. Before 2008, the Kosi already carried a reputation for movement. Emerging from the Himalaya, it delivers enormous sediment loads onto a broad fan. Over centuries, its channels have occupied many positions across that fan, leaving a visible archive of former routes. Embankments built in the 20th century constrained the modern channel. Confinement can protect land from frequent movement, but it also keeps sediment inside a narrower corridor. The riverbed can continue to erode while the surrounding fan remains lower. On the 18th of August 2008, the Kosi breached an embankment near Kosi in Nepal. The breach connected the river to an older channel path. Water turned away from the engineered course and spread across Bihar. Satellite images made the state change unmistakable. The pre-flood channel curved well to the east. The post-breach flow cut south through terrain that had not carried the main river in modern decades. This was not just water beside a river. It was a river network occupying a different branch. The flood was catastrophic for communities in its path, but the mechanism is not captured by calling it an unusually large overflow. Sediment, confinement, inherited channels, and a breach work together. The disaster emerged from the landscape's stored alternatives. No single threshold number predicts the exact day of an avulsion. Structures fail locally. Flood hydrographs differ. Channels are surveyed imperfectly. The useful prediction is conditional. Where is the river raised? Where are the low roots? And what connection would let feedback take over? The Kosi also shows why old maps are active data. A pale abandoned channel on a satellite image is not merely geological history. It is a low-resistance corridor that can matter again. Roads and settlements may cross it because no main river has occupied it within living memory. Risk, therefore, sits in the gap between human memory and landscape memory. The floodplain can remember pathways much longer than institutions, property lines, or protective structures do. Look at a large delta from above, and it resembles a fan of overlapping tongues. Those shapes are not decorative coastline. Each lobe records a period when the main river delivered sediment through that route and built land around its mouth. A new channel reaches open water by a relatively short path. Sediment spreads and the lobe grows. As the mouth advances, the route lengthens. The channel gradient decreases. Deposition shifts upstream, and another route may eventually become shorter. Then the river avulses. The active mouth jumps. Sediment supply to the old lobe collapses, while a new lobe begins to grow elsewhere. Over thousands of years, repeated switches construct the delta as a mosaic of active and abandoned pathways. The lower Mississippi has occupied several major delta lobes during the last several thousand years. The modern Birdfoot Delta is only the latest arrangement. Its long engineered course projects far into the Gulf, while older pathways spread west across Louisiana. Avulsion is therefore both destructive and constructive. It can flood settled land in the new path, yet it is also one of the natural processes by which sediment reaches different parts of a delta. Holding the river in one route concentrates benefits and costs in different places. The delta remembers every switch. Trace the lobes backward, and the coastline becomes a timeline. One river, many former mouths, each built until the network found a more advantageous exit. Near central Louisiana, the Mississippi passes close to the Atchafalaya River. From there, the Atchafalaya offers a shorter, steeper route to the Gulf. Left alone, more flow entering that path can make the path still more efficient. Human changes helped open the connection. In the 19th century, a cutoff altered the old loop linking the Mississippi, Red, and Atchafalaya rivers. Through the following decades, the Atchafalaya enlarged and drew an increasing share of water. By the mid-20th century, engineers concluded that the Atchafalaya could capture the Mississippi's main flow. That would not merely move a blue line. It would reorganize navigation, water levels, sediment delivery, and the river-dependent infrastructure extending to Baton Rouge and New Orleans. Congress authorized the Old River Control Project, completed in 1963. Its structures regulate the connection and prevent capture. The operating objective maintains the established distribution of flow between the Mississippi and Atchafalaya systems. On a diagram, the job looks simple. Measure the incoming river and hold the branches near a target split. In the physical river, every gate opening changes velocity, scour, sediment transport, and water surface slope. The controller is embedded inside the system it controls. The structure does not remove the Atchafalaya's gravitational advantage. It supplies an opposing constraint, continuously preventing a route switch feedback from completing. The difference in route length is not a decorative fact on the map. A shorter descent to sea level means more slope is available over each kilometer. More slope can support faster flow and greater erosive power. That is the same local feedback from a small breach, scaled to a continental river junction. The control complex sits where a line on a national map is negotiating with gravity every day. Its purpose is to make the longer path remain the dominant one. Old River Control is not one little dam. It is a complex of channels, gates, an overbank structure, an auxiliary structure, a navigation lock, and a hydroelectric plant. Together they meter an enormous moving load of water and sediment. The control problem begins with observation. Engineers track discharge through the Mississippi and Atchafalaya system. Gates adjust the connection so the annual flow distribution remains near its authorized balance. In the flood of 1973, the low sill structure was pushed far beyond ordinary conditions. Scar undermined parts of the foundation. Concrete walls shifted. A wing wall collapsed. The structure held, but the episode exposed how a controller can approach its own threshold. Open a gate and more water enters the shorter route. More water increases erosive power. Scour can deepen the approach and outflow channels, making the hydraulic connection more effective. The gate setting and the riverbed evolved together. The response was not to declare the system solved. An auxiliary control structure added capacity and redundancy. Monitoring, maintenance, and floodways became layers in a nested defense. This is systems engineering at landscape scale. The machine holds one network state while the river continually modifies the wiring beneath it. Success is not a permanent equilibrium, it is an actively maintained condition. Redundancy changes failure behavior. If one structure is damaged, another route can pass water. If discharge rises beyond the ordinary control range, floodways can reduce pressure elsewhere. But every layer also adds dependencies. Gates need power and access. Approach channels need stable beds. Measurements must remain reliable during floods, and decisions must arrive before hydraulic feedback accelerates. The system is strongest not when nothing can fail, but when one failure does not immediately become total capture. If a major river changes course, the first consequence is obvious. Water arrives where it was not expected. The less obvious consequence is that water leaves places built around its presence. Along the old route, water levels can fall. Navigation channels may require different dredging. Industrial intakes, drinking water systems, ports and wetlands depend on particular ranges of flow and salinity. A weakened freshwater river can allow salt water to push farther inland. Along the new route, flow and sediment increase. Flood stages change. Banks erode. Existing bridges, levees, pipelines, farms, and towns encounter a river with a scale their local channel did not previously carry. Now connect the map. Grain moves from interior farms to river terminals. Refineries and chemical plants cluster along deep navigation corridors. Wetlands receive or lose sediment. One branch switch propagates through transportation, water, energy, and ecological networks. That does not mean a Mississippi capture is forecast for a particular year. The control complex exists precisely because the risk is managed. Honest systems thinking separates a mechanism from a countdown. A possible state change is not the same as an imminent one, but the consequence map explains why the control effort is so large. Holding the river is also holding a web of downstream relationships in their current geometry. Those relationships respond on different clocks. A flood wave moves in days. Shoaling can disrupt navigation over months. Salinity and wetlands adjust seasonally. Ports, pipelines, and cities take decades to relocate, if they can relocate at all. The physical river can switch faster than the economic network can adapt. That mismatch in response time converts a geomorphic event into a system shock, even far from the point where the first bank failed. Levees reduce frequent flooding along the protected corridor. They also disconnect the river from much of its floodplain. Sediment that once spread widely can remain in the channel or travel farther downstream. Where deposition continues inside confinement, the bed and flood level can rise relative to the protected land. Stronger containment can therefore increase the contrast between ordinary stability and the consequences of a rare breach. Downstream, keeping sediment in one navigation channel can starve other parts of a delta. The active route extends while abandoned or disconnected wetlands receive less material. Control changes where the landscape is allowed to rebuild. Sediment diversions attempt a more flexible strategy, open selected pathways so water and sediment can build land without surrendering the entire river course. That is still a control problem. The timing, location, ecological effects, and navigation trade-offs matter. There is no single setting that maximizes every goal. A fixed channel favors established ports and communities. A mobile river distributes sediment. Flood protection, navigation, land building, and ecosystem change pull the system in different directions. The important shift is from control or no control to state management. Which branches are allowed to carry flow? Which thresholds are monitored? Which failures are contained? And which landscape changes are planned rather than accidental? Better management begins with measurements that correspond to the mechanism. Bed height relative to the floodplain, channel depth, sediment flux, water surface slope, scour near structures, and the capacity of alternative pathways. A single water level gauge cannot describe all of that. The useful dashboard is layered. It watches the slow variables that store risk as carefully as the flood peak that may release it. Otherwise, the system looks safe right up to the moment its map changes. Strip away the place names, and an avulsion has a simple shape. A slow process builds stored advantage. Sediment raises the present route. Old channels preserve alternatives. A flood creates a connection. Then feedback chooses. More water in the new path causes more erosion. More erosion lowers resistance. Lower resistance attracts more water. At the same time, the old path loses transport power and begins to fill. The final map depends on history. Without the abandoned channel, the breach might drain back. Without aggradation, the new route might not be steep enough. Without confinement, sediment might have spread somewhere else. The switch is sudden, but its causes are layered through time. That pattern appears beyond rivers. Networks keep using an established route until cost accumulates and an alternative crosses a threshold. Then traffic, capital, species, or information can reorganize faster than the background conditions changed. A river makes the pattern visible because it redraws the ground. The old channel remains as a scar. The new channel deepens into a fact. Between them lies the moment when a small breach became a new system. The next time a river looks like a permanent border, remember what the map hides. The line is not the river. The river is water, sediment, slope, memory, and a set of possible paths. Most of the time, one path wins quietly. Sometimes the whole landscape watches another one take over.